The first goal of today is the introduction of normal neighborhoods and normal coordinates. We know that the restricted exponential map has a differential at 0, which is invertible because it's the identity. So we can apply the inverse function theorem and deduce that there exists a neighborhood V of 0 in TPM and a neighborhood U of P such that the restricted exponential map defined on V with values on U is a diffeomorphism. So now we are ready to give definition of normal neighborhood of P. So a neighborhood U of P which is the image under the restricted exponential map of a star-shaped neighborhood of the origin of TPM is what we call a normal neighborhood of P. On this neighborhood, it's possible to define spatial coordinates with respect to which the metric and the Christoffel symbols have a special property. In order to construct these coordinates, we observe the following fact. Every orthonormal basis B1, B2, Bn of TPM induces a basis isomorphism that will be denoted by B, and it is defined by this formula B of x1, x2, xn, this is equal to xi bi. So here I am using the Einstein convention. Now we suppose that u equal exponential map image by the exponential map of V. This is a normal neighborhood of B, and then we can combine this map with B in the following way. We want to construct some coordinates on U. So we need a map from U to Rn. The idea is that we combine a map from TPM to Rn with a map from U to TPM. This map is the inverse of B, and this map is the inverse of the exponential map restricted to V. And we call this phi. So phi equal B inverse composed with and this goes from U to Rn. These coordinates are what we call normal coordinates centered at P, also Riemannian normal coordinates centered at P. I want to present their properties. The first one is their uniqueness. So we have this proposition which says the following. Suppose that Mg is a Riemannian manifold, P is a point of M, and the U, exactly as before, is a normal neighborhood of P. Then for every normal coordinate chart on U, excuse me, centered at P, the coordinate basis is orthonormal at P, and for every orthonormal basis B1, B2, Bn of TPM there is a unique normal coordinate chart x1, x2, xn 1u such that di at p is bi for I varying from 1 to n, where n is the dimension of the manifold, and any two normal coordinate charts x1, x2, xn, x tilde 1, x tilde 2, x tilde n are related by this formula x tilde j. This is aj I xi, where this is a orthogonal matrix, where A belongs to On. How to prove this? So suppose that phi is a normal coordinate chart on U, and by definition we have that this is P inverse composed with exp P inverse, where B is the isomorphism induced by an orthonormal basis B1, B2, Bn of TPM. Now let's make the following observation. What is the differential of the inverse of pi at P? This is the differential of the exponential map at 0 composed with the differential of B at 0, and this is linear. Sorry, since B is linear, this coincides with B, and this is the identity, so this is equal to B. Consequently, what is delta I at P? This is P pi inverse P of delta I at 0. It is B of delta I at 0. But B is an isomorphism which send delta I to Vi. And this identity here proves that the basis formed by delta I is orthonormal because the Bi are orthonormal by hypothesis. Conversely, if we have an orthonormal basis, B1, Bn of TPM, we can define then the isomorphism B, and the normal coordinate chart phi equal B inverse composed with the inverse of the exponential map. And the computation we made here proves that this is true. Now suppose that phi tilde equal to B tilde inverse composed with the inverse of the exponential map is another normal coordinate chart we want to prove the relation between the x tilde I coordinates and the xi coordinates. So what we will do? We take phi tilde composed with phi inverse and we get that it is given by this composition. So this is a composition of two isomorphisms, two basis isomorphisms, and precisely it's a linear isometry implies the associated matrix belongs to On. So we get that such a relation is true, and from this identity we deduce that x tilde I is equal to xi for any I equal 1 to n, if and only if A is identity, and this means that the normal coordinate chart associated with a given orthonormal basis, which means associated with the isomorphism B induced by that basis, is unique. Because in that case, from this formula you would get the identity, because of B tilde and B would be equal. The second proposition is about the other properties of normal coordinates. So suppose that u x1, x2, xn is a normal coordinate chart centered at P. Then we have that the coordinates OP are 0, 0, 0, B, Gij equal delta Ij at P, C, for any V equal Vi delta I in TPM, the geodesic gamma V starting at P with initial velocity V is represented in local coordinates which are normal, by TV1, TV2, TVN. For t in some interval I, with 0 in I, and gamma vi contained in U. D gamma I, j, k at p equal to 0 for any I, j, k, and E all partial, or sorry, first order partial derivatives of Gij vanishes at P. Okay, let's prove this proposition. So A says that the statement A says that the coordinates of P are 0, 0, 0. So x1, x2, xn are given by B inverse composed with this map. So you just observe that phi p is a B inverse this is a 0, and the B inverse of 0 is a 0, 0, 0, where this 0 here is a vector in TP. How to prove this? This follows from previous proposition. Precisely, we have proved that di p is a orthonormal basis, and this means that G P of DIP EJP equal delta EJ, which is exactly this. Now we have to prove C. It is the representation in coordinates of a geodesic having initial velocity vector equal to the vector having v1, v2, vn as components with respect to this basis here is tv1, tv2, tvn. This is consequence of the fact that this geodesic is given by this map. So when you try to find the local representation of this geodesic, what you do is to find phi composed gamma v, which is B inverse and this is exactly TV1, TV2, TVN. Now we have to prove that the Christopher symbols vanish at P. So let V equal VI TIP, an arbitrary element of TPM. Let's write down the geodesic equation for gamma VT, which has this expression. Since these maps are linear in T, the geodesic equation reduces to gamma I, j, k, gamma t, gamma vt times gamma v I prime, gamma v j prime equal to 0. And this is equivalent to say that gamma ij k tv, the derivative with respect to t of the ith component is just vi, and similarly the derivative with respect to t of gamma vj is vj. Now it's enough to evaluate at t equals 0 so we get gamma I j k at 0 Vi Vj equals 0, and this is true for any value of k and for any v in TPM. The fact that this is 0 can be proved choosing appropriately v. So if v is dA, then you get that gamma A k at 0, this is 0. Here I'm not using the Einstein convention. What I did here is just taking I and j equal to A. For proving that a similar statement holds true when the bottom indices are different, you take V equal delta A at P plus delta P at P, and you do this for any pair of indices A and B, and then you subtract you will get gamma A B K at 0 equal to 0, and this is the end of the proof of B, because the point of coordinate 0 is P. Now we have to prove that the first order partial derivative of Jj are 0 at P. In order to do this, we use the proposition about the characterizations of metric connections precisely statement C, which says that Ek Gij is equal to gamma Kil Glj plus gamma Kjl Gil, where this is a smooth local frame. Now we take Ek equal delta K in order to get delta K Gij, and now we observe that this is 0 and this is 0 at P. A word about the terminology. Geodesic starting at P and lying in a normal neighborhood of P is called radio geodesic. The reason of this is that in local coordinates, if v is the initial velocity vector, this is tv1, tv2, tvn, where v is vi delta I p. The second goal is to try to understand what are the geodesics of the model spaces. The easiest case is the 1 over n Okay, first of all, we observe that constant coefficient vectors are parallel this follows from the fact that the covariant derivative along a curve in the Euclidean space is a simple expression. And Euclidean geodesic are consequently straight lines. It follows from here. A curve is a geodesic if the velocity vector is parallel. This says that the velocity vector must be a constant coefficient vector, and a curve which has a velocity vector which is a constant coefficient vector is a straight line. Remember that it is necessary to have constant speed parameterization. It is also clear that every maximum geodesic is defined on the entire real line R, and this statement is in general reformulated as follows. Every Euclidean space is geodesically complete. What about spheres or radius R in the Euclidean space? In order to determine the geodesic curves of this manifold, we define great circles as a subset of the form SNR intersection pi, where pi is a two-dimensional linear subspace. So this means that a great circle is the intersection of S and R and a two-dimensional plane passing through the origin of Rn plus 1. This means that a great circle has a radius equal to R. It is useful to mention the corollary 5.2, which says that if M is an embedded submanifold, then gamma is a geodesic with respect to the tangential connection which is the connection, the Levi-Civita connection on M, if and only if gamma second is orthogonal to this tangent space for any t in I, where I is the interval of definition of gamma. Okay, so let's try to use this information to prove the proposition which describes the maximal geodesic curves on spheres of radius r. So a non-constant curve on SNR is a maximal geodesic if and only if it is a periodic constant speed curve whose image is a great circle, and every sphere is geodesically complete. How to prove this proposition? Let's fix a point P in SNR, and let's prove that TPSNR is vectors which are orthogonal to P, where in this sentence I see P as the position vector of the point P. In order to do this, we consider the affine function of the sphere, that is f of x equal to the length of x square, and what we need to do now is to compute the differential of f at P acting on V, where V is a vector in this tangent space, which is also tangent to the sphere. It's possible to prove that this differential is 2 times this inner product, and this is 0 if and only if V lives in TPSN R. If you want to prove this statement in this formula, take a generic smooth curve starting at P with initial velocity vector V. Then the composition of V with this curve that I will call gamma is a constant function, because this function is a constant on a sphere, and I am assuming that the curve lies entirely on the sphere. Then it makes sense to compute f composed with gamma prime at 0. This is exactly the f PV, and this is 0 if and only if V is tangent to the sphere. So this says that V is tangent to the sphere if it is orthogonal to the position vector of the point P that I denoted by the same symbol, and this is the proof of this identity. Now let's erase maybe this part. Now, suppose that V is in TPSNR, then we can define A equal length of V over R, V hat as V over A, and this implies that the length of V hat is R. Now we consider gamma defined on R with values in Rn plus 1, defined this way. It's easy to compute that gamma t belongs to S n R for any t in R. So this is a curve lying on the sphere. Gamma prime t is this. and gamma second is this. It is immediate to observe that gamma second t is given by minus a square gamma t and this implies that gamma second t is orthogonal to t gamma t s n r. The reason why this is true is that you have to think gamma t as a vector value map. So this is now a function which is vector value. For each t, the endpoint of the vector gamma second t belongs to the sphere, and this means that this vector is orthogonal to the vector tangent to the curve. Sorry, tangent to the sphere. So this vector is orthogonal to the sphere, and these are vector tangent to the sphere, so they are orthogonal. So corollary 5.2 that I recalled before applies. That gamma is a geodesic on SNR. And it is easy to see that this is true. So gamma coincides with gamma v, which is the notation that we use for geodesics starting at p with the initial velocity vector equal to p. Now let's observe that gamma v is periodic of period 2 pi over a, and has a constant speed. This is true, for example, by a simple computation. Look, for example, at gamma prime t. This is a spatial linear combination of two vectors of length r. This is a vector, the position vector p, which has length r, and this is a vector of length r by construction. It is also clear that gamma v belongs to the linear space spanned by p and v at. So Gamma V is a great circle because it belongs to the sphere and belongs to a two-dimensional linear subspace. Then conversely, a great circle given by S and R intersection pi where pi is spanned by VW. Precisely, VW is an orthonormal basis. Then the great circle is the image of the geodesic gamma V, where V is exactly this vector here, such that gamma V0 is RW. Now let me check how much time I have. Not that much. What about the hyperbolic spaces? We have this proposition which says that a non-constant curve of the hyperbolic space is a maximal geodesic if and only if it is a constant speed embedding of R whose image is one of the following. A. In the case of the hyperboloid model, the intersection of H and R with two-dimensional linear subspace of R n, 1. This is called great hyperbola. B. In the Beltrami-Klein model, the interior of a line segment whose endpoints lie on the boundary of K and R. K and R is the symbol we use for the Beltrami-Klein model of the hyperbolic space. See? The interior, Poincaré Beau model. The interior of a diameter of B and R, or the intersection of B and R with Euclidean circle that intersects the boundary of B and R orthogonally. D. Poincaré half space model the intersection of UNR with a line parallel to the y-axis or a Euclidean circle with center on the boundary. So maybe it's a good idea to try to make a picture so in the case A, you have to take the upper sheet of the hyperboloid used in definition of the hyperbolic space. Suppose it is this. Of course, here I am considering the case n equal 2, so I'm working in R21, and you consider the intersection of this hyperboloid with a plane passing through the origin. This will determine a curve on this hyperboloid, for example this one, which is an hyperbola. For the second case, you have that the geodesics are the interior of segments of straight lines, like this. In the third case, you have that geodesics are the diameters or pieces of circles intersecting orthogonally the boundary of B and R. And in the last case, you have that geodesics are half-lines like this, or they look like this. I think it's a good point where to stop. I will sketch the proof of this result next time.